So here's another really challenging integral, and because of the length of the solving process, I went ahead and I rewrote everything beforehand so that I could just briefly walk you through how to solve this integral. So we're looking at the integral of x cubed plus 4 all over x squared minus 1 times x squared plus 3x plus 2 dx. Now, for this integral, we're going to have to use partial fraction integration, and really what that means is we're going to have to simplify the denominator into its into its smallest terms. And what I mean by that is we can modify this function so that it's the integral of x cubed plus 4 all over x plus 1 times x minus 1, which we got from this x squared minus 1. And when we simplify this function right here, this polynomial, what we get is x plus 2 and x plus 1. Now, you'll notice that if we combine these two x plus 1 terms in the denominator, we can simplify the equation further so that we have the integral of x cubed plus 4 all over x plus 1 squared times x minus 1 times x plus 2 dx. And here's really where the partial fraction integration begins. Really what we have to do is we have to find a way to reduce this entire this polynomial fraction into discrete smaller fractions. And when we do that, we can take apart the integral and then solve each one individually. The reason why we'd want to do that is, of course, because it's a lot easier to split apart these integrals and solve each one of these four individually than it would be to try and find some kind of u sub or other method to solve this integral. And so the first step that we have to do is we have to break this fraction apart based on the terms that are found in the parentheses within the denominator. So since we have a repeating term right here of x plus 1, we have to build up to it, which means that we have a over x plus 1 plus b over x plus 1 squared, which is what we had originally right here, plus c over x minus 1 plus d over x plus 2. And now we're going to step away from the calculus part of this, and we're going to talk about how we're going to find these terms a, b, c, and d. And what we'll start by doing, and this is the case in all partial fraction integration problems, is we have to multiply both sides of this statement by the denominator of our original function in terms of x with the numerators. So when we do that, you'll see that this cancels out everything that we have in the denominator here, and these terms that we have over here, the x plus 1 squared times x minus 1 times x plus 2, are going to be distributed to all four of these fractions, and that's essentially going to put it in a form that we can actually work with. And what that looks like is this. We should have x cubed plus 4 is equal to a times x plus 1 times x minus 1 times x plus 2, and that is because when we multiply this entire part, you'll see how x plus 1 squared gets stuck in the numerator of the a function, and we can simply cancel out one of these squares and the denominator, and what we'll be left with is a times x plus 1 times x minus 1 times x plus 2. That's the reasoning behind this setup right here. We'll also be left with b times x minus 1 times x plus 2 plus c times x plus 1 squared times x plus 2 plus d times x plus 1 squared times x minus 1. And now this is really where the creativeness has to come in with partial fraction integration, because we have to select numbers, we have to select values for x such that we'll be able to solve for each variable a, b, c, and d individually. And it's not always the case that this will work. You can always set up a system of equations. This just happens to be a faster method that in fact works for this problem. And what I've done here first is I've let x equal 0. And when we let x equal 0, what we have is, and I've highlighted in orange everywhere I've replaced our x's in the original function with 0. We have 0 cubed plus 4 is equal to a times 0 plus 1 times 0 minus 1 times 0 plus 2 plus b times 0 minus 1 times 0 plus 2 plus c times 0 plus 1 squared times 0 plus 2 plus d times 0 plus 1 squared times 0 minus 1. Now, you'll notice that we actually haven't canceled any terms, but we've maintained all four of them, which is going to work to our advantage later in the problem. And for now, we just have to keep in mind that this statement, this statement of 4 is equal to a times negative 2 plus b times negative 2 plus c times 2 plus d times negative 1. This statement is going to help us find the value of a later on in the problem. So next, what we have to do is we have to find a way to solve for each of them individually, as I said before, and we can go ahead and solve for b by letting x equal negative 1. And I'll let you go ahead and look at the algebra here. And what we end up getting when we plug in negative 1 in all of these x terms is 3 is equal to a times 0 plus b times negative 2. It's kind of hard to see there, but this in fact is negative 2 plus c times 0 plus d times 0. And as you can see, we've canceled out a, c, and d, which allows us to solve for b. 3 is equal to negative 2b, or in other words, b is equal to negative 3 halves. Now let's go ahead and solve for d. To solve for d, we're going to let x equal negative 2, and when we plug in the negative 2 to all of our x values here, we are left with negative 4 is equal to a times 0 plus b times 0 plus c times 0 plus d times negative 3. Or in other words, we've just canceled out a, b, and c, and we're now able to solve for d. Negative 4 is equal to negative 3d, or in other words, d is equal to 4/3. To solve for c, we're going to go ahead and let x equal 1, and when we plug in 1, we'll find that 5 is equal to a times 0 plus b times 0 plus c times 12 plus d times 0. Or in other words, 5 is equal to 12c, which allows us to find that c is equal to 5/12. Now, remember that equation that I was telling you that we have to keep in mind? We're going to be using that one right now to solve for our value of a, and this was our original statement in the very beginning, where I said we'll find a later, and I went ahead and copied it down here. We have 4 is equal to a times negative 2 plus b times negative 2 plus c times 2 plus d times negative 1, exactly as we've written up here. And when we go ahead and plug in our solved values for b, c, and d, we'll find that we actually now have the entire equation in terms of a and other constant values. So we're able to solve for a, and what we get is that a is equal to negative 3/4. And now we've pretty much done the partial fraction parts of the integration, and all that's left is to plug in those values to the original function. We had the integral of a over x plus 1 plus b over x plus 1 squared plus c over x minus 1 plus d over x plus 2 dx, and we can now plug in those values, as I've said, and begin to solve this integral. I went ahead and did it on another page because I was running out of space here, but once you copy all of that information down, you will get that the integral is we're finding the integral of negative 3/4 over x plus 1 minus 3/2 times x plus 1 to the negative second power, or in other words, I turn this into multiplication from a fraction, which would have looked something like this: negative 3/2 over x plus 1 squared. And instead I moved the square value up to the numerator by having a negative exponent, plus 5/12 times 1 over x minus 1 plus 4/3 times 1 over x plus 2 dx. After solving each of these integrals individually, and since we know we can do that because we have separate functions that are separated by plus and minus signs, we find that our answer is equal to negative 3/4 times the ln of the absolute value of x plus 1 plus 3 over 2 times x plus 1 plus 5/2 times the ln of the absolute value of x minus 1 plus 4/3 times the ln of the absolute value of x plus 2, and we can't forget our constant plus c.